Assalamualaikum and good evening. This is my presentation video. First, I will introduce myself. My name is Muhammad Firdaus bin Norizan. My matrix number is B01710065 and my supervisor is Encik Mahasan bin Man Ali. In this video, I will present about my presentation PSM2. My title for this project is to design enhancement of pedal fin for fishing kayak. The introduction is based on background study of project. In recent years, kayak manufacturer has been modifying their existing recreational kayak to accommodate user desire of using their recreational kayak as watercraft for fishing. Next, the pedal fin drive system has been used in modern fishing kayak to increase the speed performance as well providing good stability. The different type of aerofoil has their own performance characteristic. Hence, this is a need to conduct a research to investigate the type of aerofoil design that can be applied to the pedal fin drive to optimum the thrust performance. Next, the problem statement. There are two types of pedal fishing kayak, which is propeller and fin. This project focuses on pedal fin of fishing kayak. Different type of aerofoil design can be applied to the pedal fin, which is can produce different characteristic performance. Next, this problem statement is to investigate the other type of aerofoil design that can be used to maximize its performance. The first objective is to investigate different types of aerofoil design that can be applied to the pedal fin drive. Second, to develop viable prototype of pedal fin drive that integrate with different types of aerofoil. Third, to validate the type of aerofoil with an optimum forward thrust for fishing kayak. First scope is identify on the different type of aerofoil design with the focus on NACA 0015 symmetrical, NACA 2214 symmetrical, and NACA 4415 chamber. Second, using SolidWorks software to develop a viable prototype of pedal fin drive with the chosen type of aerofoil design. Third, using NC software to validate the type of aerofoil in which give the forward thrust for fishing kayak. Next, this is some literature review about the investigate the type of aerofoil for this project. The first methodology is observation on previous article journal focused on NACA 0015 symmetrical, NACA 2414 semi-symmetrical, and NACA 4415 chamber. Second methodology is design on SolidWorks software. Create modeling fin with airfoil NACA 0015, NACA 2414, and NACA 4415. And third methodology is analysis on NC software to identify the modeling and matching the direction, static pressure, velocity magnitude, coefficient lift, coefficient of drag, and lift force. As the first step for creating the airfoil model, the data of airfoil was taken from the NACA database. Table show the NACA database of NACA 0015 was located. Those coordinates of airfoil were saved in Excel. Then data of NACA 0015 profile were imported to SolidWorks software and the model was generated. Detail of NACA 0015, max thickness 50% at 13% chord and max chamber 0% at 0% chord. Next, the step for creating the NACA 2414 airfoil model. The data of airfoil was taken from the NACA database. Table show the NACA database of NACA 2414 was located. Those coordinates of airfoil were saved in Excel file. Then the data of 2414 profile were imported to the SolidWorks software and the model was generated. Detail for NACA 2414, max thickness 14% at 29.5% chord and max chamber 2% at 39.6% chord. Furthermore, this step also for creating the NACA 4414 airfoil model. The data of airfoil was taken from the NACA database. Table show the NACA database of NACA 4414 was located. Those coordinates of airfoil were saved in Excel file. Then the data of NACA 4415 profile were imported to the SolidWorks software and the model was generated. Detail of NACA 4415, max thickness 15% at 30.9% chord and max chamber 4% at 40.2% chord. This part shows how to simulate a NACA 0015. The coordinates are tabulated from which the following profile is drawn as in figure 1 and figure 2. In this step, the coordinates for NACA 0015 airfoil were imported to create the geometric shape that will be used for the simulation process. The mesh mode is shown in figure 4. After mesh analysis is found that total nodes are 2564 and total element is 2360. The figures show the visualization of static pressure contour distribution around the NACA 0015 at 0° angle of attack. Since it is symmetrical in nature, velocity magnitude of airfoil is same on above upper and lower layer on the airfoil. Since the velocity is the same, the pressure on the upper and lower layer will also be same. From the simulation of static pressure and magnetic velocity of NACA 0015, the data coefficient of lift, coefficient of drag, and lift force of NACA 0015 were found for different angle of attack. Finally, the ratio of CL to CD was calculated. The table shows the data CL, CD, and LF with different angle of attack. Next, this part is about the plotting graph. Graph 1 is about the coefficient lift, graph 2 coefficient of drag, and graph 3 about the lift force of NACA 0015 with different angle of attack. Next, this part shows how to simulate a NACA 2414 airfoil. The coordinate are tabulated from which the following profile is drawn as in figure 1 and figure 2. In this step, the coordinate for NACA 2414 airfoil were imported to create the geometric shape that will be used for the simulation process. The mesh mode is shown in figure 4. After mesh analysis is found that total nodes are 3134 and total element is 2859. At zero angle of attack, it can be seen that the static pressure is little higher on the lower surface than on the upper surface. This generates a pressure gradient which causes a force on the total surface area on the airfoil. As the angle of attack increases, the pressure difference between the upper surface and the lower surface increases, thus causing an increase in the force, which causes increase in lift and drag coefficient. Velocity magnitude of airfoil is little higher on the upper compared to the lower layer of the airfoil. Next, from the simulation of static pressure and magnetic velocity of NACA 2414, the data coefficient of lift, coefficient of drag, and lift force of NACA 2414 were found for different angle of attack. Finally, the ratio of CL to CD was calculated. The table shown the data CL, CD, and LF with different AOA. Next, plotting the graph. Graph 1 is about coefficient of lift, graph 2 about the coefficient of drag, and graph 3 about lift force, the airfoil NACA 2414. In addition, this part shows how to simulate a NACA 4415 airfoil. The coordinates are tabulated from which the following profile is drawn as in figure 1 and figure 2. In this step, the coordinate for NACA 4415 airfoil were imported to create the geometric shape that will be used for the simulation process. The mesh mode is shown in figure 4. After mesh analysis is found that the total nodes are 4055 and total element is 3735. Next, this static pressure contour and velocity magnitude for NACA 4414 is close to NACA 2414. At zero angle of attack, it can be seen that the static pressure is a little higher on the lower surface than on the upper surface. This generates a pressure gradient which causes a force on the total surface area of the airfoil. As the angle of attack increases, the pressure difference between the upper surface and the lower surface increases, thus causing an increase the force and which is causing increase in lift and drag coefficient. Velocity magnitude of airfoil is a little higher on the upper compared the lower layer of the airfoil. Furthermore, from the simulation of static pressure and magnetic velocity of NACA 4415, the data coefficient of lift, coefficient of drag, and lift force of NACA 4415 were found for different angle of attack. Finally, the ratio of CL to CD was calculated. The table shows the data CL, CD, and LF with different AOA. Next, plotting the graph. Graph 1 about the coefficient of lift, graph 2 about the coefficient of drag, and graph 3 about the lift force of NACA 4415. Next, comparison result of NACA 0015, NACA 2414, and NACA 4415. From the graph 1, it can see that The starting lift coefficient is nearly same for all the three airfoil, but with increase in angle of attack, NACA 2414 show higher lift coefficient at value 0.8215 at angle of attack 7.5 degree compared with NACA 0015 and NACA 4415, while the NACA 4415 has higher stall of angle at 13.5 degree. Next, it is clear from the graph 2 that NACA 2414 has a higher initial value of drag coefficient at value 0.10698 at angle of attack 0.7.5 degree compared with NACA 0015 and NACA 4415, while the NACA 4415 take overdue to its wide range of angle of attack at 13.5 degree. In addition, from the graph 3, it can see that NACA 2414 can generate very high amount of lift coefficient at value 38195.4 at angle of attack at 6 degree as compared to NACA 0015 and NACA 4415. Next, the conclusion and recommendation. The conclusion. This report was done within its time planning by the topic through this project running within the problem statement, objective, scope and limitation that belong to this project. The first objective that has been achieved is to investigate the different type of aerofoil design that can be applied to the pedal fin drive. The second objective that has been identified is to develop the variable prototype pedal fin drive and integrate with different type of aerofoil. The third objective that has been identified is to validate the type of aerofoil with optimal forward thrust for fishing kayak. After finish generate the fishing fin design with different type of airfoil in SOLIDWORKS software, the design of fin was imported to NC software to continue the analysis in this project. Next, the recommendation. The project has been done completely. There are some points that can be applied on the future to improve the performance and design of pedal fin. Firstly, added more type of airfoil in this project to get more data and result. Next, for design the pedal fin, trying to change or improve the shape of the design. Another recommendation is using another software in order to achieve the main objective of this project. That's all from me. Thank you.